This question is about the drift speed of electrons in a copper wire. Assume the drift speed is 4.0 times 10 to the minus 4 meters per second in a particular copper wire. We want to know on average what is the electron current in this wire. In other words, how many electrons drift past a given point in the wire every second. We're also given that the radius of the wire is 4 millimeters. All right, so first let's analyze the situation just so that we understand the geometry of it and what's happening. I'm going to draw a portion of a wire here, which is a cylinder. And at one end of this cylinder, we're going to have a cross-sectional red circular boundary. Now, a bunch of electrons are inside the cylinder. And there's a current happening, so the electrons are going to be moving. Now what I'll draw is another piece of this same wire. And what's going to happen is all the free electrons in the left half of the wire are going to drift over time to new locations. They're all going to pass through this red boundary. And we want to identify what is the electron current I, it's called, in electrons per second. Now, first of all, it's worth noting that copper has a free electron density of 8.5 times 10 to the 28th free electrons per cubic meter of the conductor's material. That's something that can be looked up in tables or perhaps on google.com, for example. And this is the value for copper, and other metals could have different free electron densities as well. For the segment of wire that I've sectioned off here, I'm going to call its length delta x. And it's also going to have a volume delta V, and I'll call its cross-sectional area A. We were also given that the radius was 4 millimeters. Now, from the geometry of this cylinder, we can see that one way to express the volume would be by multiplying the area times the length. We also have this idea that the number of free electrons in any segment of a conductor will be equal to the free electron density of that conductor material times our conductor's volume. So if we were to do a substitution here, we could take this portion, A delta x, and substitute it in to make this expression. And interestingly, if we want to go farther, we can divide both sides. By time. Now, if we recognize that delta x over delta t is the drift speed, then we can go even farther with our substitutions and plug in our drift speed in place of delta x over t. And there's one more thing we can recognize too, that N over delta T is the electron current. That's its formula. With these substitutions, we get a new formula for electron current. And this would be the one to use for this problem here. Let's plug in. I get an electron current of 1.7 times 10 to the 21. And the units of this would be electrons per second. And that'll be our answer. This is the number of free electrons that are drifting through that red circular boundary every second. Now we'd like to turn it into a current, though, which is capital I instead of little I. In a previous video, I had showed that the relationship between current and electron current is capital I will be little I times the elementary charge E. So we'll take our electron current and multiply it by 1.6 times 10 to the minus 19 coulombs. When it comes to this problem, I'm not interested in the direction of the current. I just want the size of it, so I'm not going to worry about any negatives that would be involved here. I get 273. The units will clearly be coulombs per second, which is also equivalent to amps, capital A, or amperes. That is the unit of electric current.